Hi everyone, thanks for clicking and welcome back to my channel. Today, we'll be talking about airspeeds. Indicated airspeed, calibrated airspeed, equivalent airspeed, true airspeed, ground speed, and last but not least, Mach number. We will discuss what each one of these speeds mean and how to convert from one to the other, and which ones are more important to us as pilots. So without any further ado, let's dive right in. Firstly, let's talk about the most basic one that most of your aircraft performance is based on, the indicated airspeed. Well, the IAS, or indicated airspeed, is not actually a speed, it's rather the amount of dynamic pressure the airplane is experiencing in the air. To help understand IAS, let's first see how the IAS is measured. The indicated airspeed is measured by the pitot tube and the static port. The pitot tube is a small tube protruding into the wind, and it is usually placed under the wing in light general aircraft and near the nose in large transport category aircraft. As the aircraft flies through the air, the wind flows around the aircraft as well as into the pitot tube. This air we refer to as total pressure. What is total pressure, you may ask? Is dynamic pressure plus static pressure. Dynamic pressure is the pressure created by the movement of a body, or in our case the airplane, through the air. And as for static pressure, is literally just the outside atmospheric pressure. As you can see on the screen in front of you, the pitot tube senses dynamic pressure plus static pressure, or total pressure. And static port senses only static pressure. Inside the ADC, or the air data computer, where all the corrections and measurements are made, the static pressure readings cancel each other out, and we are left with the dynamic pressure. This dynamic pressure is what we call IAS, or indicated airspeed. This indicated airspeed is purely a direct reading of dynamic pressure, excluding any error corrections such as position error, temperature, compressibility, etc. We will look at these errors shortly. One more thing to keep in mind before we move on to the next airspeed is that the airspeed indicator will always indicate a reading as long as there is air flowing through the pitot tube. Meaning, even if the aircraft is stationary on the ground and there is air or headwind blowing through the pitot tube, the airspeed indicator will indicate a reading. Now, let's talk about the calibrated airspeed. Well, as I mentioned earlier, indicated airspeed is merely dynamic pressure. It is needed to know our stall speed, Vx, Vy speeds, VO, approach and touchdown speed in various configurations, and so on. However, we cannot use it directly to determine, for example, how fast we are traveling, or time required, and ETAs, and so on. The indicated airspeed is measured by pitot tube. The pitot tube's position is never perfectly and flawlessly aligned as it should be. That's why the pitot tube is accompanied by an error we refer to as position error or instrument error. Once this error is corrected for automatically within the ADC or air data computer, we get CAS or calibrated airspeed. It is literally indicated airspeed calibrated for position or instrument error. Next, equivalent airspeed. Equivalent airspeed is calibrated airspeed corrected for compressibility error. At low altitudes and airspeeds, this error is almost negligible. However, at or above Mach 0.4 or 40% of the speed of sound, the calibrated airspeed becomes to get affected by compressibility caused by the pressure waves created around the aircraft. Thus, a correction is necessary to account for such errors. So calibrated airspeed corrected for compressibility gives us equivalent airspeed. Now, before we move on to the TAS or true airspeed, please keep in mind that these two, calibrated airspeed and equivalent airspeed, are not usually used or needed directly by pilots. You may think of them as two bridges to move from indicated airspeed to true airspeed, which are more important to us. Let's have a look at TAS or true airspeed. This is the first actual speed we are going to look at. TAS is the speed of the aircraft through the air. Remember, TAS is the airspeed of the aircraft through the air, not across the ground. We obtain TAS by applying density error corrections to the equivalent airspeed. Density is the effect of both atmospheric pressure and temperature. Both altitude and temperature cause true airspeed to increase. You may ask why? The answer is simple. At altitudes, or high altitude, and in hot temperature, air molecules are far apart from each other, causing the aircraft to experience less drag, with those air molecules resulting in the airplane to travel faster. Until now, if you have noticed, all these airspeed that we have looked at, only TAS is an actual airspeed. But still, we cannot directly use the TAS to figure out our ETAs and the time required en route, etc. In order for us to do that, we need our speed across the ground, which is our next point. Ground speed. Ground speed is how fast we are moving across the ground. If we need to determine how long it will take us from one airport to another, it is the ground speed that we must use. Now, how do we calculate ground speed? We need TAS to do that, which we can easily get from the AFM, Airplane Flight Manual, or the POH, Pilot Operating Handbook, depends on what you prefer to call it, on the actual weather condition, and apply the current winds aloft, meaning the true airspeed plus or minus wind, we get the ground speed. With ground speed and distance, you can easily get the time. Last but not least, Mach number. The Mach number is the ratio of the speed of an object, in our case the airplane, to the speed of sound. Flying at Mach 1 means you are flying at exactly the speed of sound, or also known as sonic speed. Flying below Mach 1 at about 0.8 to 0.9, this is the Transonic region. And flying at more than Mach 1, like most fighter jets and the Concorde, you will be flying at supersonic. Flying at above Mach 5 is the hypersonic region, and only missiles and rockets can reach that speed. Mach number is an important quantity to compare the speed of an object with the speed of sound. It is a parameter that denotes the speed of a flying object in air medium. Now, why is it important? As we climb higher, say flight level 330 and above, the air pressure decreases exponentially, and there are fewer air molecules in the air. Thus, if we climb at a constant indicated airspeed, the true airspeed increases. As the true airspeed increases, the airplane starts to approach the speed of sound of Mach 1. Although most of, if not all, modern jet airliners nowadays don't reach Mach 1. Now, even approaching Mach 0.86 or so, the airflow at some points around the aircraft actually reaches Mach 1 before the aircraft itself reaches Mach 1. Remember, the air flowing on top of the upper camber of the wing. It accelerates, thus it can reach Mach 1 before the aircraft does. When the airflow reaches Mach 1, keep in mind now that the aircraft itself is still below Mach 1. A shock wave starts to form above the wing. This shock wave creates a huge amount of drag and causing the center of pressure to move aft of the center of gravity, which results in a phenomenon called as Mach tuck or tack under. This is a rapid pitch down moment caused by the shock wave. And in order to avoid all of that, aircraft manufacturers during test flights determine a specific Mach number at which the onset of this phenomena will occur. And it is the value that is referred to as Mach crit, or critical Mach number. It is the Mach number at which the airflow at some points around the airplane will reach supersonic before the aircraft itself does. So we fly Mach number and we keep an eye on it all the time while flying at high altitude in order to avoid reaching Mach crit. Now, here is a formula on how to calculate your Mach, although which with today's technology the aircraft does it for you. So the Mach, basically the ratio between the true airspeed and the local speed of sound. And the local speed of sound is 39 square root of the temperature in Celsius plus 273 degrees. Lastly, I need you guys to know the relationship between indicated airspeed, true airspeed, and Mach number with altitude. As you can see in front of you, if we climb at a constant indicated airspeed, both TAS and Mach will increase with altitude. Also, if we climb at a constant true airspeed, indicated airspeed will decrease with altitude. However, Mach number will increase. This is why at the crossover altitude, roughly about flight level 280 to flight level 290, more or less, we switch from climbing based on indicated airspeed to Mach number to avoid inadvertently reaching Mach crit. Just remember this graph and it will help you figure out a lot of ground school questions. And also to give you an idea to visualize in your head the effect of altitude on both indicated, true, and Mach number. Alright, ladies and gentlemen, this brings us to the end of this video. Should you have any questions or suggestions, kindly feel free to leave them in the comment section below. And until the next video, see ya.